Proved by principle of mathematical induction (P.M.I) that 1 plus r square plus r raised to power n is equals to 1 minus r raised to power n plus 1 divided by 1 minus r. So for r not equals to 1, if r is equals to 1, this will be 1 minus 1 and that will be 0. So and the denominator cannot be 0, so it will be undefined. So r is not equals to 1. So to prove this by principle of mathematical induction, so we have step 1. Show that the given statements is true for n equals to 1. Now, to show that the given statement is true for n equals to 1, so take note of the series here. So this series, this one is A0 and this one is A1. So that means the first term is 1 plus r, because the first number you see here is when n is 0, as in for this one. So the combination of first and second is when n is 1 for this series. So now to test for if for the given statements to be true, if n is 1, so that means I will consider these two together, because if I say it is 1, so that means that place is just n equals to 0. So now left hand side is equals to 1 plus r. Remember, if you say 1, that means n is 0 there. So if n is 1, so it will be 1 plus r. For n equals to 2, it will be 1 plus r square, like that. So we are proving for n equals to 1. So that means left hand side is 1 plus r. So right hand side 1 minus r raised to power n plus 1 divided by 1 minus r. So if n is 1, so this is 1 minus r raised to power 1 plus 1 divided by 1 minus r. So this is 1 minus r raised to power 2 divided by 1 minus r. So if you look at the numerator here, it is difference of 2 square. So what I have there is like saying 1 square minus r square divided by 1 minus r. So that is 1 plus r, 1 minus r. Remember, this is difference of 2 square. So that will be 1 plus r, 1 minus r divided by 1 minus r. So 1 minus r will cancel out, so which is equals to 1 plus r. So meaning it is the same thing as the left hand side. So that means left hand side and right hand side are equal. So we can now say the given statement is true for n equals to 1. So that means we have shown step 1 like this. So now let's show step 2. Step 2. Assume that the given statement is true for n equals to k. So assume that the given statement is true for n equals to k. So for n equals k, so you rewrite everything here and replace your n with k. So that means this becomes 1 plus r square plus r raised to power k is equals to 1 minus r raised to power k plus 1 divided by 1 minus r for r not equals to 1. So we only rewrite all this and replace all the n with k. So that is for step 2. So after you have done that, then you have to conclude so that the given statement is true for n equals to k. So like that. So now for step 3, so we have small manipulation there. So now step 3, using the assumption made in step 2, show that the given statements is true for n equals to k plus 1. So using the assumption made in step 2, so show that the given statement is true for n is equals to k plus 1. So I'll start with left hand side. So the left hand side we have 1 plus r square, then plus r raised to power n. So this will be equals to, remember I said in this step just put brackets here and here. So that means this left hand side is the same thing as 1 plus r square plus r raised to power n. So it's like I'm rewriting this one, but I just put brackets. So that's it. So that is the left hand side, so it's equals to this. Now if you look at what you have in the brackets here, it is like what you have here, but it's not complete, it stops here. So you have to complete it by adding the r, but now in terms of k. So that is how you add, you complete it in terms of k. So this will becomes 1 plus r square, then plus r raised to power k. So you have to complete it. So in terms of k, so then plus r raised to power, so k plus 1. So remember we are doing for k plus 1. So this n will be k plus 1. Yeah. Let me change that. So now this n is k plus 1. Remember, we said using the assumption made in step 2, show that the given statement is true for n equals k plus 1. So that means as I write all this, so I have to replace that n with k plus 1 like that. And the second step is just put brackets here. So that's what I did here. Then I still have this outside. R raised to power k plus 1. So in the next step, all this expression here is like what you have here, but we need to complete it plus r square r raised to power n. So that is what I write here. So to complete this, but you add r raised to power k to it. So then I have r raised to power k plus 1 outside. Now all this series, now if you compare with this series, the result is 1 minus r raised to power n plus 1 divided by 1 minus r. So that means all the series here now will be the same thing as 1 minus r raised to power k plus 1 plus 1, because n is k plus 1. So that will be our result there. So let's show that in next step. So next step now, all the series here, the expression here is this results now. So that means this will becomes 1 minus r raised to power k plus 1 divided by 1 minus r. So that will be the sum of this series, yeah, which is this. So n will just turn to k, because what I have here is in terms of k. So plus r raised to power k plus 1. So like that. So what are we going to do here? So we can find the LCM. Remember, this is over 1. So find the LCM there. So this will becomes LCM is 1 minus r. So 1 minus r in 1 minus r is 1 minus r. So that is times 1 minus r in 1 minus r is 1. So times the numerator. So that will be 1 minus r raised to power k plus 1. Then plus 1 minus r divided by 1 is 1 minus r. So 1 minus r times this. So that will be 1 minus r, then r raised to power k plus 1. So like that. So what we have next? So another step. So this, we can split this using law of indices. So 1 minus r raised to power k times r, because r is r raised to power 1. So r raised to power k times r raised to power 1 is r raised to power k plus 1. There. So plus 1 minus r raised to power k plus 1. Everything over 1 minus r. So another step. So the numerator now, what is common? You will notice this is 1 minus r here, but you can't factor it out here. So what are we going to do here now? So just expand this bracket. So this will be 1 minus r raised to power k times r raised to power 1 plus, so expand, so 1 times r raised to power k plus 1, so that is r raised to power k plus 1, then minus r times r raised to power k plus 1, everything over 1 minus r. So what do we do here? So we only expand, that is 1 times this, then r times this. So we expand the bracket there. So if we do that, the term will cancel out. So by splitting this, I thought it would be useful. So but now I can see that 1 minus r raised to power k plus 1 plus r raised to power k plus 1 minus r into r raised to power k plus 1. So I've turned this back to the index form, that is law of indices. This is r, this is r. Take 1 and add the power. So you may leave it as k plus 1. So it's different simplification I'm thinking before. So 1 minus r. So if you have this now, you will notice that this will cancel out this. So we are going to have so we'll have 1 minus r brackets r raised to power k plus 1 left divided by 1 minus r. So now remember, this r is power 1. So that will be like r raised to power 1 times r raised to power k plus 1. So if you use law of indices, the base are equal. So that will be r raised to power k plus 1 plus 1. So that is what I will have there. So this will becomes r raised to power k plus 1 plus 1. So like this. So from here we already know that, so n is equals to k plus 1. So when n is k plus 1, then replace all the k plus 1 back with the n. So when n is k plus 1, so we have 1 plus r square plus r raised to power n, that is this k plus 1, will be equals to 1 minus, be equals to 1 minus r raised to power, so this is k plus 1 here, it will be n. So r raised to power n plus 1 divided by 1 minus r. So this have give us back this series. So that means we have proof using induction. Therefore, you conclude the given statements is true for n is equal to k plus 1. So that means we have proved like this. So final conclusion now. Therefore, final conclusion. Therefore, this is true by principle of mathematical induction. So proved.